introducing Peter. So Peter is a CDO and co-founder of the software company DeepBlue, which I assume we'll hear about today, and lecturer in computer science at the University of Sussex in the UK. His research is on program analysis and automated verification. He co-developed the 2LS and JBMC verification tools for C and Java, and is a regular contributor to CBMC. With DeepBlue, he develops tools for making software developers' life easier, in particular in the area of unit testing for Java applications. So, Peter, thank you for agreeing to giving us this talk, and the stage is yours.
Good, thank you, Ofer. I hope everybody can hear me well. So this talk is about some aspects of experiences that we made at DeepBlue in the last couple of years in applying automated test generation to large Java code bases. And so we all have a desire for software that has fewer bugs. In this talk, we will focus on software that is not safety critical, but business critical. And there are lots of great techniques that have been developed in the formal methods community and other communities to help developers write more bug-free code and make developers' lives easier. And so often we talk about challenges that prevent more widespread adoption of automated verification techniques, such as scalability and state space exclusion. However, there are other obstacles too, and I'm going to talk about one of them today. So when I talk about business critical software, then I mean any part of a software stack of an enterprise that it needs to perform its daily operations. So bugs in the software have tremendous impact on revenue, customer satisfaction, reputation, competitiveness, and so on. And obviously, companies are under constant pressure to deliver features ever faster and cheaper. And defects should be detected early in the development process to keep the cost of fixing them low. So the cost of a bug that causes damage to a customer is orders of magnitude higher than a bug that the developer notices before they commit the code into the code base in the first place. So this thinking is not much different from what we're used to in safety critical domains. And testing plays the key role in detecting defects and ensuring high quality levels. So however, there are different sorts of tests that play different roles. So in order to shift left the defect detection, tests are needed that can run early in the development process. So these tests must be fast enough so that developers can run them on their machines on every pull request. So having a solid base of unit tests is best suited to deliver this. Integration and system tests are essential, but if you have too many of them, then they cannot run continuously anymore on each pull request. So what we do at DeepBlue is to develop automated test generation tools that help developers to write such unit tests more efficiently. So DeepBlue has been improving its test generation tool, DeepBlue Cover, over several years. And typically, we measure achieved code coverage over several benchmark projects to measure our progress. So however, we noticed that there are some projects which seem to resist any tool improvements. And a couple of months ago, one of my colleagues asked me, what's wrong with one of the projects there? None of the improvements seems to show effect. And he said, could we even write tests manually for it? And this was a great idea. And so I looked at a challenging method in that code base and tried to write a unit test for it manually. And after 2 hours, I gave up because the setup was very complex. And there were lots of dependencies that I didn't manage to mock out. And this was not the only method that caused trouble. So we needed a way to figure out where the particular challenges in these code bases are. And if we couldn't improve the tool to deal with these methods, then we should at least be able to tell the user why we were not able to produce a test. So this colorful picture that you see here is actually a map of that code base that I was able to produce months later. And so each box is a method and its size is proportional to the lines of code. And the green colors indicate that the method is supposed to be unit-testable. Red colors indicate that there are some testability challenges, and yellow colors mean that the test is very trivial, like a getter or a setter. So something you wouldn't usually write a test for. So if I had such a map back then, it would have been obvious that this code base has certain challenging areas. So I'm going to talk about how we can build such maps and what we can potentially learn from them. And because these issues also apply to other automated verification techniques, not just test generation. And if we want to apply these techniques to larger enterprise applications, then we need to be aware that there are certain obstacles around testability and aim at finding solutions for them. So these code bases are very high value assets for any company, and they are constantly being improved and adapted to business needs. So any automation support that we can provide can deliver high impact. And so testability issues, deficiencies are a huge issue, and this is nothing new. So design for testability has been a concept for many decades, but it doesn't seem to be fully standard practice yet. So approaches such as TDD are generally picking up, but the main business priority remains functionality, and that needs to be delivered as fast as possible. So before we go into details, let's clarify some terminology. So what is a unit test? So different people mean different things. Some people would even consider every test written using the JUnit framework unit test. Obviously, you can write any kind of test with it. So this is not quite what we mean by it. So for this talk, a unit test tests a simple scenario, usually a single method call on a small testable unit such as a class. And typically such tests have 3 sections. So there is an arrange section that sets up the inputs and mocks, an X section that calls the actual method on tests, and then a search section that asserts the effects. So dependencies to other subsystems are usually mocked. External dependencies such as socket connections are definitely mocked. So for example, it may not talk to a database. So tests are expected to run very fast so that they can be run by every developer on their machine. And they have no effects on other tests so that they can be run in parallel without interfering. So this is very schematic to give you some key to how to read these tests. Real-world tests look more like this, but one can still identify the 3 sections to some degree. So there's a very lengthy range section, which is quite typical. Then these methods down here these are the X section essentially. And then there's assertion down here that checks the result. So not all code in the code base is equally critical. So when you ask software architects and engineering managers, then they are primarily concerned with having tests for the really critical business logic. So our main goal is to have tests for that critical code, because this is what people care about. So for a developer on a code base, it is quite self-evident what is critical and what isn't. But for a tool, it is not. So many people use cyclomatic complexity as a proxy for spotting where the hard parts are. And on the right-hand side here, you actually see a complexity map of the Apache Tika code base. So it's a document processing library. And the less green and more red, the more complex a method is. So you'll see that some methods that are highly complex. So we won't use cyclomatic complexity. Instead, we use a very simple analysis to identify really trivial codes such as getters and setters. Yeah, for those methods, you wouldn't typically write explicit tests, but you need them anyway to set up objects and access the state when you write assertions. So everything else that is not super trivial, we consider is critical, and we don't make a judgment about how critical this is. This is left to the developer. So once we know the code that we consider critical, we'll distinguish between unit-testable and not unit-testable. And we perform an under-approximation of the not unit-testable code. So method might be classified as unit-testable, although they actually have testability challenges. But we don't want to have too many false alarms here. So beyond that, one could also look at the existing tests, evaluate the composition, unit versus integration versus system tests, measure the coverage, adequacy, and so on. But this is not part of this talk, so we'll focus purely on the testability part. And if you're interested how a coverage map would look like, so you have here the corresponding coverage map for TICA. And you see they have actually made quite an effort to test the critical parts here. So there are many of the complex classes up here are actually quite well covered, with some exceptions, of course. So what does testability mean now? So Nate Edwards from IBM wrote 1975 on software testability. If modularity is controls so that the function of a module is independent of the source of its input, the destination of its output, and the past history of use of the module, the difficulty of testing the modules and structures assembled from modules is greatly reduced. So in other words, the more modular, functional, less coupled, less stateful, the easier it is to test. So then Ray Friedman makes this a bit more precise and defines testability as an application of Kalman's observability and controllability concepts to software. And he also says that if it can be shown that a testable program doesn't exhibit any input-output inconsistencies and supports small test sets, and outputs are easily understood. And he also mentions that you can have metrics that assess the level of effort required in order to modify a program so that it becomes testable. And a third quote from Robert Binder a couple of years later really puts this into a nutshell. So testability has two key facets, controllability and observability. And to test the component, you must be able to control its input and internal state and observe its output. If you cannot control the input, you cannot be sure what has caused the given output. If you can observe the output of a component under test, you cannot be sure how a given input has been processed. So there are the two main aspects, controllability and observability. So roughly speaking, controllability in a control system means that I can steer it in any desired state. So for software, this means the ability to arrange the inputs of a method on a test to make it take a desired code path. And also the ability to control the effects of dependent components, which I will call mockability here, and I will explain this on the next slide. So what affects controllability? So non-determinism, because I want essentially anything that talks to operating systems, such as network, file system, getting the system time, random generators, multi-threading, and so on. So these are things that if I want to have a deterministic test, I will have to mock. And also unreachable code that cannot be exercised, so I cannot drive the system into exercising that code. So observability in a control system means to be able to determine the state from its output. In the context of software testing, is the ability to write assertions on relevant effects of the method on the test. So if we can't write assertions, then we can't check whether the behavior is correct or wrong. And observability is affected by the lack of accessibility in the sense of encapsulation. But there's also a relationship to mockability that we'll see in a second. So what is mockability? So this is a bit more folklore knowledge, and I'm trying to make this notion more explicit here. So mockability is the ability to inject objects that must be mocked in order to control and observe the interactions. So mockability is at the core of the testability notion that we use here, as it affects not only the controllability, but also the observability. So let's have a look at controllability part first. So we have on the left here a product class and a method to add an expiry date, which is 30 days from now. And a method to check whether the product has expired. So the corresponding test would look as this one here on the right. So, but how can we actually test the is expired true case? So obviously we don't want to add this because this would not be really viable. So we have a problem here, and to test this properly, we need actually to mock the timestamps here. So fortunately, the Java library provides us with the clock class, which allows us to control what the local date time now actually returns. So this means that we can mock it, provided that we make the dependency on this clock explicit. So we must be able to inject this clock into the code to be able to control the behavior. And so with this injected clock here, so we are actually able to write any test case we want for this around this is expired method without relying on the passage of time. So this test is much more robust than anything that would use sleep or anything like that. So now let's have a look at another quite common pattern that shows how mockability relates to observability. So here we have a app class that has a client to send a message to some remote service. And there are two problems here. So first of all, we don't want to use the real client here, because we don't even have the service that it will talk to. And there is not really anything that we can observe about this method. So writing a meaningful test here is difficult. So let's do the following first. So let's make this client injectable. So this brings us a step closer to observability, which means now we can, in principle, we can assert something about this client. But we still use the actual client. So the next step is that we have to mock the client. And after mocking this client, we can actually assert something about it, because we can check whether this send method has actually been called with the message. So this has brought us a step closer. In addition to that, we can, since we now can control the behavior of the client, we can now also exercise this catch block here. So we can actually say, okay, the client should throw an exception. And then we could write an assertion that checks whether this exception has been thrown. Not quite, unfortunately, because the exception is swallowed here. And yeah, so we would have to do some more improvements to the testability of this code here to actually write a test for that with appropriate assertions. So what you see here, these are very common problems in code that we see every day, and these are code that hasn't been really written with testability in mind on that level has these sort of challenges. So to summarize a bit more abstractly what is going on. So what we have on the left here is we have the class under test. And on the right, we have a test class. And so we'll look now at the data flows between the arrange and assert sections of the test and the method under test that we want to exercise. So we have in yellow flows that concern controllability. We'll have in purple flows that concern observability. And these kind of greenish boxes here, fields and call dependencies, so these essentially capture the side effects that we also have to observe. So the first thing is in the arrange section, we set up the inputs for the MUT. So we use controller methods such as setters to set fields. We pass arguments to the method on test, and we must also be able to inject the mocks for dependencies that we want to mock. So next thing is the method analysis might modify some fields, and we want to observe effects, these side effects. So we need observer methods such as getters, and then we can write assertions about those in the assert section. Then when we call a mock dependency, then we can observe which arguments are passed to this mock dependency, and it can assert on them in the assert section. The behavior of the mock, so the mock outputs, is something that needs to be set up in the range section. And then at last we can write assertions about potential return values and exceptions. So if the controllability flow is broken in some place, then this means we have trouble setting up the range section probably. If the observability flow is broken somewhere, then we have trouble writing reasonable assertions about the code test. Good. So many papers about testability also talk about testability metrics. So the goal here is to find actually correlations between software quality metrics and the difficulty to write this. So to make quantitative predictions about the effort required to write tests. So our goal here, however, is to give precise diagnostic information. So we want to tell the user for each method what and where the problem is, and assisting in fixing it, and potentially aiming at fixing it automatically. So it's not only possible for human to write better tests for the code, but also for our test generation tool to perform better. Good. So for this purpose, we implemented a static analysis that works on the Java bytecode. And we, as said, we under-approximate the notions of not valuable to unit test and not unit-testable. And we analyzed 40 repositories with a few hundred modules. So in total, it's around 8 million lines of code in the repositories themselves and 89,000 classes. We also have to analyze the dependencies, which makes the amount of code that we actually have to look at in order of magnitude larger. So these repositories are from various areas like business workflows, data processing, distributed computing, and data storage. So the analysis that we have to implement essentially follows the data flows that we described in this model. And to give you one example, so we have a mockability analysis, and that we use to under-approximate the set of non-mockable methods. So a method is called non-mockable here if, so this is now inductive definition of non-mockability, if it must be mocked because it's something that is non-deterministic. So this is the base case. And then if it has a call to a non-mockable static method or a non-mockable instance method on an object that is non-injectable. So we need a second analysis that actually tells us when an object is non-injectable, which essentially means that it cannot be supplied through any input. So it is not controllable. And a similar analysis needs to be done for observability. So what did we get? So on average, we got that 21% of a code base is not unit-testable. And this is for various reasons that I roughly categorized here in observability reasons or file system operations, network operations, and other things like random generators, time, and so on. 6% are not valuable tests, so these are is trivial stuff, and 73% are considered unit-testable. So the first two are under-approximations, actually. And so you see here that there's quite the variability between these projects, and essentially each project has somehow its unique characteristics to some degree. So smaller projects tend to be more extreme than larger ones. And larger ones are closer to the mean. So if you look at these data on module level, then it's even more extreme. So you see modules, you essentially see a variance from 0 to 100% on in each of these categories. So it could be that some modules just share similar characteristics because they contain similar code, or they just suffer from similar testability issues. So when aggregating over different types of software, there is not actually that much difference that you observe here. One could argue that proportional data processing has a bit more file system, problem mocking file system operations, whereas data storage is a bit more networking. Yeah, so it seems business workflows is slightly less testable. Yeah, but this could just be because these are applications that are slightly less mature than, for example, databases. So this is there's not that much difference here. Yeah, interpretation. Yeah, one can make different interpretations here. But as I said, the primary value that we want to have from this is the diagnostic information on the method level. And to give you an example here, kind of diagnostic information that we can produce at the moment. So this is one method that in a mail service that tests the connection to the mail server. So it's kind of a similar pattern to the client service example that I had before. And so what we get for this is, yeah, so they calls the methods that should be mocked because they perform file system operations, but we cannot mock them. And you get essentially kind of a stack trace that tells you traces back to the root cause here. In this particular flow here, the root cause is that we open a file descriptor. So in this example, actually, everything is about this mail sender that we have to inject here if we want to mock it. And there's even a private method here that creates this mail sender, but unfortunately it's private, so we cannot mock it without trying to break encapsulation.
Peter, can we interrupt for questions, or you prefer questions only in the end?
We can interrupt this.
So if I may ask, what can the user do about the fact that the function is not mockable?
So I'll come to this later, it might be clear.
Okay.
So essentially you have to address the controllability and observability of the problems. And this diagnostic information is intended to help you to guide you towards it. So what we give you at the moment is a stack trace that tells you, oh, this is the root cause of the problem. We have to look at this Java mail sender implement instance here. And yeah, you'll see, okay, if you want to mock this call here, I will have to inject a mock. I must be able to inject a mock for this instance.
Okay.
You can give more detailed suggestions, even the potential suggestions of patches, how to fix this in future. Is something we would like to do. Yeah. So, so some limitations. Yeah. So obviously this is not really quite an exact science. So the analysis itself can be made sound, but it relies on lots of assumptions. So what is considered mockable and observable, and so on, depends on who you talk to and what is considered acceptable in unit tests. For example, Java allows many dirty tricks to hack around restrictions. For instance, you can use reflection to drill holes into encapsulated objects. That way you can call private methods, for example. And so whether this is acceptable depends on your coding styles and habits and how much you care about maintainability and in the end, how big the pressure is to make certain things work. Another way is to use bytecode manipulations. So this essentially means rewriting the binaries to make the code testable. So where this is acceptable, that the code that is tested is actually not the same as the code shipped. Yeah, again, depends on what the alternatives are. And it's certainly not recommended practice, I would say. So also drawing the border between unit tests and integration tests is not always that easy. So talking to a database is probably not a unit test anymore. Having multiple threads might be admissible sometimes. Reading files might be generally fine. Writing files is probably more debatable. Yeah, so which leads us to the aspect of what should be mocked. So file system manipulations are not always that clear-cut. So network should probably always be mocked. Threaded code may have sorts of issues, so it might be distinguished there. Time and random generators usually are mocking. But even there, so there might be situations where it's fine to have some mocking, as long as the test oracle remains deterministic. So there's quite a lot of subjectivity there, and how you do this analysis, and depending on who it is, what kind of developer it is, and what the specific circumstances are, the analysis might need to be adapted to specific situations. So what are the implications on test efficiency? So if you have lack of unit testability, then this leads to an imbalanced testing pyramid. So essentially, if the pyramid the other way around. So you have a higher proportion of system integration tests, which leads to slow CI, and then you might not be able to run all the tests on each pull request. So you select some tests, run the remaining tests in nightly rounds. Then if this fails, somebody has to invest extra effort into fixing a bug that made it into the code base. Well, if you ran all the tests, it wouldn't have made it in the first place. So this does not really satisfy the goal of shift left. So this is why unit testability is so important. So what about coverage metrics? So as I said, people really want to focus on critical code coverage. So if projects have between 5 and 40% trivial code, as I've seen in my analysis, then it's relatively easy to trick code coverage numbers and add 10% without actually adding any real value. And so if you have 80% code coverage target, then this doesn't mean much if the remaining 20% is actually code that you really, really want to test. So you really have to focus on the critical code, and this testability analysis can point you to certain areas of risk that require special attention. Good. So as mentioned, there are common workarounds to make the code more testable. So byte code rewriting is one of them. Another way is not to write unit testable, to write higher level testable with all its consequences. I've mentioned a reflection to a workaround of observability. Some people also do some ad hoc weakening of encapsulation, so making private things public and so on. What I've also seen quite often is, yeah, if nothing works, then you write assertions on the log file content, because this is, yeah, I think this is very bad practice. Leads to further reduction of the code quality. So what should actually be done is you should consider the requirements of the testing interface when designing the functional interface, so that you don't run into these issues in the first place. And so when talking to companies, the test-first approaches, such as test-driven development, are actually quite popular, and many teams want to adopt them. Of course, even if they successfully adopt it, this has only immediate impact on the fresh code, whereas the effects will be much slowly on the big pile of existing software. So what are implications on automated verification tools? So when we apply automated verification to large software, then we usually do it in a divide and conquer fashion. So we write harnesses that verify the individual parts. These are actually quite similar to unit tests, except that instead of using concrete values, we use non-determinism and assumptions. And for the assertions, we usually have more general post-conditions. So this is quite similar to what actually automated test generation produces. It produces such harnesses, but then instantiates them concretely. So unless you have a verification tool that has a God almighty view on the unit under test, you will run into similar problems of observability and controllability. So in another idea that could be derived from this testability analysis is to have something like a verifiability analysis. And this could, for example, map out the code base into parts where it's practically impossible to handle, parts for which we know the tool has certain limitations. We already know about them, so we don't expect much in these areas. And there are other parts where actually the tool expects to deliver results. And so similar to us, where testability is a tool for communication with the customer to spot expected issues early, manage expectations, and then help the customer to fix these issues. For a verification tool, so when you apply to a large code base, so this could give some indications where to start, where the easy parts are, where the difficult parts are, what are the upper bounds on what a verification tool can actually be expected to achieve. So back to testability. So a couple of months ago, a customer evaluated our tool on some code, and it struggled with some parts of the code base. So fortunately, they were able to share the code with us. And a colleague of mine had a look, and he refactored the code a bit to see whether this improves the situation. And it actually did, it performed better. So we then explained to the customer what we did and why. So it would have been really great if I had such analysis back then. It could have shown to the customer immediately what the problems are, why no test is generated, and they might even have been able to fix it themselves without our support. So now months later, I have such functionality, and I ran the analysis on the original code. So this is what you see here. And you see there's quite a lot of red parts. I then ran tool on the refactored code, and the results actually more interesting than I expected. So my colleagues' refactoring that greatly improved the performance of the test generation tool had effectively improved the testability quite a lot. So there is much more green now in this picture. And what he essentially did is he improved injectability to control non-determinism, and improve the observability of some relevance effects to be able to write assertions. So this was actually quite interesting, and it's applied after the fact to see actually refactoring the code is actually visible in this analysis quite significantly. Good. So to summarize the takeaways, so business software is often business critical, and there is a drive to increase unit testing levels in order to be faster than the competition. And people only care about testing the really critical parts of the code, and thus the code coverage needs to be normalized to those. So not all code is equally easy to test, and testability analysis can determine where issues with controllability and observability are present in the code base, and also tell you why. So testability issues may also have impact automated verification tools. And it would be interesting to see whether there's something possible to do about automated refactoring, maybe some kind of synthesis or similar to automatically improve testability in the future. Good, thank you. And I'm happy to take some questions now.
So thank you, Peter. So yeah, we're open for questions now. Yeah, Georg.
I'm just wondering how many of these problems are actually down to object-oriented programming, and if switching to a more functional style wouldn't solve many of these issues.
This is true to a certain degree. So there are in particular, the observability issue, which is minor in what I have seen, is an object-oriented programming problem. The injectability, mockability problems, depends. Yeah, so switching to a more functional style certainly helps. The problem is those code bases are there. They are large, they have high value, they run the business essentially, so you can't replace them overnight. So this is a work for decades to port these code bases to a more functional state.
Okay, any more questions? If not, I have a question. This type of analysis is not really suitable for in-process testing, right? It's more for testing like legacy code or like offline, right? It's not like something that you would operate on a daily basis in a software company.
So this is what developers do in their daily development. So they make changes, run these tests to see whether there have been regressions, write new tests to cover new code, change code, and so on. And this is why these tests need to be fast. So these tests are essentially they're run daily, thousands of times.
So you reached a point where the same developers that develop the code also know how to operate the tool then?
Yes, exactly. So the tool that we offer, there is a IntelliJ plugin, so essentially an ID plugin that the developer can use themselves. There's also a CLI tool that can be integrated into the CI process.
Okay, thank you. Any more questions? We are actually 10 minutes early. So if there are no more questions, so we'll just create an artificial coffee break, even if you drank too much coffee today. And we'll just meet in 10 minutes, I suppose.
Thank you.